Hello. We have been looking at magnets, and one of the things that we noticed when we were looking at our first magnet experiments was that if we took a magnet and we brought it near a coin, it wouldn't do anything. It wouldn't attract it at all. However, if we took a magnet and we brought it near a paperclip, it was attracted to the paperclip. So what we're going to look at now is why some things, some objects are magnetic. So here we see that we have a very standard model. We would usually call this an orbital model. We have the electron moving in an orbit around a nucleus. And what we notice when we look at this image is that the electron is moving in a circle. And so the current, the capital I current, is moving in the opposite direction. And so what we see is this figure shows a simple classical model of an atom in which a negative electron orbits a positive nucleus. And so in this picture of the atom, what we notice is the electron's motion is that of a current loop. So we could just take our fingers and use our right hands and follow our fingers around the direction of the current, and our thumb would then point in the direction of the magnetic moment due to the electron's orbital motion, which is what we see right here. So an orbiting electron acts as a tiny magnetic dipole with a north pole and a south pole. So let's look at that in a little more detail. So this arrow here represents the inherent magnetic moment of the electron. So if the electron is spinning, it has an inherent magnetic moment. An electron's inherent magnetic moment is often called the electron spin because in a classical picture, a spinning ball of charge would have a magnetic moment. And while it may not be spinning in a literal sense, an electron really is a microscopic magnet. So here, let's look at an image where we have a full piece of matter with lots of electrons within there. And each of those electrons have their own electron spin. And you see that when you have a typical element, these electrons are all pointing in different directions. So for most elements, the magnetic moments of the atoms are randomly arranged. So they're randomly arranged when the atoms join together to form a solid. And we see that here, when we look at that, the unpaired electrons point in random directions. So the sample has no net magnetic moment. So as the figure shows, this random arrangement produces a solid whose net magnetic moment is very close to zero. However, there are types of matter such that where we can have the magnetic moments lining up. So in this example, in iron and a few other substances, the atomic magnetic moments tend to all line up in the same direction as shown in the figure here. So here we see that the atomic magnetic moments are aligned. So the sample has north and south magnetic poles, just like a magnet. Materials that behave in this fashion are called ferromagnetic, where ferro is a prefix that means iron-like. And in French, we call iron is fer. So it's ferro, comes from the Latin for iron. Now, a typical piece of iron is divided into small regions, typically less than 100 microns in size, and these are called magnetic domains. So here are the magnetic domains. Here's one of the magnetic domains here, and we divide these regions into these magnetic domains. So the atomic moments are lined up within each domain. The magnetic moments of all the iron atoms within each domain are perfectly aligned, so each individual domain is a strong magnet. However, the various magnetic domains that form a larger solid are randomly arranged. So iron, while each magnetic domain is aligned, the atomic moments are aligned. However, there are lots of different magnetic domains throughout one solid piece of iron. Now, if a ferromagnetic substance, such as iron, is subjected to an external magnetic field, the external field exerts a torque on the magnetic dipole of each domain, like the torque that we saw in the last lecture. And what we see is that this torque, because of this torque, the magnetic domains align with the solenoid's magnetic field, because we saw a solenoid has a uniform magnetic field. So the torque causes many of the domains to rotate and become aligned with the external field. So here, what we end up with is an induced dipole that has north and south magnetic poles. The attractive force between the opposite poles pulls the ferromagnetic material toward the solenoid. So the induced magnetic dipole always has an opposite pole facing the solenoid. So the solenoid's pole is north. So the induced magnet will have a pole of the south, a south pole facing the solenoid. Consequently, the magnetic force between the poles pulls the ferromagnetic object to the electromagnet. So it actually gets pulled to the solenoid. So that is just like what we saw when we had our magnets attracting our paper clips. So now we can explain how a magnet attracts and picks up ferromagnetic objects. Electrons are microscopic magnets due to their spin. A ferromagnetic material in which the spins are aligned is organized into magnetic domains. The individual domains align with an external magnetic field to produce an induced magnetic dipole moment for the entire object. So we end up with an induced magnetic dipole moment for the entire object. An object's magnetic dipole may not return to zero when the external field is removed, because some domains remain frozen in the alignment they had in the external field. Thus, a ferromagnetic object that has been in an external field may be left with a net magnetic dipole moment after the field is removed. In other words, the object has become a permanent magnet. So we can actually see objects that become permanent magnets, especially if we have objects that are molten. If we have molten iron that comes out, such as at a mid-ocean ridge, and then it is in the magnetic field of the Earth, all the electrons will align with the magnetic field of the Earth, just like a compass does. A compass is just a little magnetic dipole that's going to align with the magnetic field of the Earth. And then they'll be frozen in time when the molten material, the basalt, the lava that's coming out of the mid-ocean ridge is hardened. And that's how we can see how Earth's magnetic field has changed over time. So that is how we have induced magnetism in objects. It's due to the electron spin.